Okay, uh, let's get started with torsion. Okay, so this is showing a cylindrical shaft which is attached to, say, a wall, and you basically apply a torque. Okay, the torque is denoted by T. This is basically a derivation which tells you what is the stresses developed in that shaft. Okay, in this case, the stresses developed are going to be shear stresses, just like there's a shear due to V we saw in the last class. There's also a shear due to torque, and that's what we'll be talking about. So the derivation here, which you don't have to know, just for completeness, I put it here, basically gives us a way to compute the shear stress gamma. So it depends on the radius. The radius is denoted by rho. Theta is the angle of twist, and the L is the length of the shaft. If you want to find the maximum shear strength, shear strain, all you have to do is put the maximum radius. So the radius is going to be the radius of the shaft. So here rho is some radius and C is the maximum radius. And that will give you the maximum shear strain. So you can see that the shear strain varies linearly with the radius. The larger the radius, larger is the shear strain. This gets us to shear stress, which is simply the modulus of rigidity G times shear strain. So here's the formula for shear strain at any radius, rho, and then this is the shear stress at the maximum shear stress due to the radius C. If you plot the shear stress as a function of distance from the center, so rho changes from 0 all the way to C in this case, then you'll see that just like the bending moment normal stress, it varies from 0 all the way to maximum from the, in that case it was neutral axis, here it is from the center, so it will linearly. If, however, if the shaft was hollow, then you will see that there will be a non-zero shear stress in the inner part of the beam, sorry, of the shaft, and maximum stress in the outer part. So that simply follows from the formula. All you do is put in the right radius, and you'll get the value for the shear stress. Okay, so that gets us to computing, relating the torque to the shear stress. This is the derivation. Basically, what comes out of the derivation is that the torque T is here. Let me just highlight this one. This is the final formula. It is basically the polar moment of inertia J times tau max divided by C. Okay, so J is the polar moment of inertia, and if you want to find what polar moment of inertia is, it's a table in the appendix which is now posted on Canvas. So you can see that appendix A18, and we'll actually see that a little bit later when we solve the problems. Okay, so with this, we will solve from problems. Again, remember, we have a couple of formulas: shear strain, shear stress, tau, and how is the shear stress related to torque. Uh, those are the formulas. So let's put them into use here. Okay, the shaft shown below has an inner and outer diameter of 4" and 6" respectively. The maximum allowable shear stress is 12 kSi. Find the maximum torque that can be transmitted by the shaft without failing. So we're given the inner diameter. So the inner diameter, I think we'll stick with the radius. So the inner radius, let's call that C. I think I'd use Ci or something like that. So Ci is half of the diameter. So Ci is 4 divided by 2, so 2 inches. So that's the radius. Radius. And the outer diameter is 6 divided by 2. That's 3 inches. The outer radius. And you're given the maximum shear stress is 12 kSi. So the question is, what is the maximum torque? So let's put T max is the unknown. Okay. Okay, so now given that, what is the formula for tau? That's only was only one thing, one formula which I wrote so far. It's basically this one. The the torque is J, T max is actually should have been, yeah, if this should have been max anyway. So T is J times T max upon C. So if there's tau max, it has to be, well, in this case, the maximum torque. So let's just put that value there. So T is J times tau max divided by C0. This is actually the max here in this particular problem. Okay, so now we have to compute these values. So tau max is an unknown, so let's keep it as it is. J, we'll compute J. The maximum shear stress it can bear, this is actually the max shear stress. This is like a design stress. It's 12 KSI. So convert that to, remove the kilo, or we can keep the kilo because then we can get the answer in kip inch, which is also another unit. So let's just keep the KS as it is. The outer diameter is 3 inches. Okay. And how do we compute J? So J, the formula for J, now this is again, if you go to A18, I'm just going to open the appendix. So you know where to look for these formulas. If you go to, it is appendix A18. So this is the same appendix as before. This one gives you polar moment of inertia as J. So if you have a circle, then it is pi d raised to 4 divided by 32. However, if you have a hollow circle, which is what this is the case, it is pi divided by 32 times d raised to 4 minus d. So the outer diameter raised to 4 minus inner diameter raised to 4. So we'll use this formula. But remember, it's in, you're given the diameter, so you have to convert to radius. Let's do that. So J is pi, I'll write d raised to 4, the outer diameter, di raised to 4, okay, divided by 32. So we just move things around. So I would put here pi divided by 32. Outer diameter is, so it'll be 2 times C0, so it's going to be 6 raised to 4 minus 2 raised to 4. That's it. Okay, so this is table 18. Okay, so this comes out, so we can, I'm going to finish this off now. Tau max is that first part, the J comes out to be 102 inch raised to 4 times 12 divided by 3. 12 by 3. Okay, so then this is T max equals 408.4 kip inch. Okay, the kip is because KSI was used for tau max, so the K comes from there, and the inch comes because what you've done here is we have used inches in this formula, not feet. So that's the answer. Just straightforward use of the formula. Questions? Should be 4 right instead of 2. 4 instead of 2. Did I do a mistake there? Let's see. Yeah, it's raised to 4, not 2. Pi d raised to 4. So polar moment of inertia, to think of it is, I think it's Weiss. Best way to think of any inertia is that it is something like y square dA. For T max, I think smaller diameter should be 4. Oh, followed the, I made a mistake there. Yes, good catch. So it should be CO3. Yeah, you're right. This should be twice of Ci. So twice of Ci, so 4. You're right. My bad. So it should be 4 times. So this is correct. So the answer here is right because I copied it straight from my notes. But yeah, this just correct this. This is 4 and 6. Good catch. Okay, let's let's solve the next problem. Okay, here is a problem which is has some elements of a new concept which I will talk about briefly, which is we talked about bending moment diagram and shear force diagram. There's something similar for torque problems, and that will come here. So shaft AB and CD, AB and CD. So these two shafts are hollow. Sorry, are solid of diameter D. My bad. Solid of diameter D, while shaft BC is hollow. So BC, this shaft is hollow. So that means put a color code there. It's easier to see it that way. This is pink. This is solid. Okay, and the inner outer diameters are given 90 and 120. The shaft assembly is subject to torques as shown. Compute a plot the torque as a function of shaft length, maximum and minimum shearing stress in shaft BC. So BC is the shaft which is hollow, and diameter of D if the allowable shearing stresses in the shaft AB and CD are 65 megapascals. Now this is the new thing which I think is important, which is you have to draw, for one, you have to draw the torque distance curve. This is very similar to MX and VX curve. So this is called BMD and SFD. Okay, there's no real name, good name for shortened name for this particular diagram. Torque torque diagram. You can call it torque diagram if you want, but nobody calls it TD or torque diagram. So I'm just going to go TX diagram. So we'll draw the torque diagram for this one, because you can see that the shafts, each of the shafts have different torques. So we need to draw that. Unless we draw that, we will not know what is the stress, the torques at individual shafts, and without that we cannot compute the shear stresses. So our first goal is to compute the TX curve. Now this is actually easier than you can think of. It's not that hard to do that, because it's so similar to drawing the Vx curve, where you take torques and you, or V's, and then you add them based on whatever sign convention you want to use, positive for up and negative for down. So let's do this. Let's start from A. This is A, and work our way to the right. So at A we have a torque of, it looks like 6 kilonewton meter. So let's assume counterclockwise is positive. Okay, here there's no real consequences of assuming any particular sign convention. You could assume anything on, usually counterclockwise taken to be positive. So this is 6, and it stays 6 till you reach B. At B, what you see is that there's a counterclockwise torque of 14. So if 6 is acting here and 4 is acting there, then the 6 adds to this 14, and 6 adds to the 14, you got 20. This is going to look weird if I draw it from here. Let me just reduce the scale. So let's just take this to be 6. This is 12. I think 20 should be here. Go here, go up here. This is 20. And that keeps going 20 till we reach, so let me call this B. It reaches C. At C, you'll see that there is a torque of 26 kilonewton meter acting in the clockwise direction, which is opposite to what we have so far. So this is going to induce a negative 26 torque. So we need to take 20, subtract 26 from it, and then we'll end up with minus 6. So it will go all the way down to minus 6 and keep going. So this will be the point C. Let me put these points here, C, and then it will go to D, and D we can see that there's a counterclockwise torque. So the minus 6 adds to the 6 to give me 0. This is T. This is my torque displacement or torque distance curve. Okay, this is important, because without this you cannot find the location of maximum shear stress, because that depends on the maximum torque. So then the question is, what is the maximum and minimum shear stresses in shaft BC? So B and C. So B is here, C is here. So between B and C, we see that the torques are the same. So torque at B equals torque at C is 20, I think it is kilonewton meter. Okay, so this is what we'll be using to compute the stress, and that's why I drew the torque displacement curve or torque shaft length curve. Maximum minimum stress in shaft BC. Now BC, remember, is hollow, so it will have, if you go back and if you remember this, what I drew for hollow shaft, the minimum stress occurs on the inner edge and the maximum stress occurs on the outer edge. The minimum to the maximum is actually directly proportional to the radius of the shaft. And then if you want to find tau max, in this case, these formulas are not useful because we don't know rigidity, nor do we know the angle of twist. The way we can compute tau max is through the torque relation. We know the torque, which is we just computed the torque. From that, we'll get tau max, and from tau max, we can use these expressions to get tau min. Okay, so that's what we'll do. Okay. So the formula we have, and actually, so for B, that B is it 1 and 2. Okay, so it's 2, part 2, part 1. Okay, so T is just this formula, J tau max divided by C. J tau max divided by C. Now this max will occur on the outer one, clearly. And then if you want to do the minimum, we can actually derive a similar expression like this. So we wrote down the ratio of min to max is Ci to C0. So min to max Ci to C0. So if you substitute tau max in this formula, you can actually get a formula for tau min divided by Ci. So it looks very similar. So you can just base it off this. If you want, you can remember these formulas or note these formulas, and you really don't need this one. This is used to derive this. It's very simple. You just take the corresponding torque and then divide it by the corresponding diameter. Okay, so now we just have to substitute. Torque is already computed as 20 kilonewton meter, 20 times 10 raised to 3. Tau, okay, we need to compute J though. J is pi raised divided by 32, T raised to 4. So let me do it in terms of the units, the variables we have written down here. So 2C outer raised to 4 minus 2C inner raised to 4, right? Outer raised to 4, the diameter outer raised to 4 minus diameter inner raised to 4. That's what I wrote down. Okay, so let's see the values. Here we have 90 for the inner and outer is 120. So 2C I is 90, 2CO is 120. And then if you want to convert it, you need to do 10 raised to 3. That's the conversion from millimeters to millimeters to meters. And then you have to do 4 times. Okay, so this uh, has to go in here. We're going to try to calculate that. Tau max is unknown. C0 is known. It is half of 120, so it's 60. And then second one is 20, 10 raised to 3 equals J tau min times half of 90, 45. And then of course I'm not, this has to be solved and subtracted. I don't think I have the answer for that. So I don't have the solution for, or the final answer for J, but I know what the tau max and tau min is. if you substitute J in the formula, you should get tau min equals 64.7 MPa and tau max equals 86.2 MPa. Okay. Okay, so that's the part two, and then part three, we need to compute, I think, the diameter if the allowable stress. Okay, so then the part highlighted in pink is the unknown diameter. We need to figure out what diameter will enable that the maximum shear stress is not exceeded. So we're given the maximum shear stress is 65. So it shouldn't exceed 65. Now, since we're given two parts, there's one part between A and B, there is a shaft between A and B, and another one between C and D. The question is which of these parts is more critical? Which of this part will fail first? If you look at the shears, the torque versus distance plot, you'll see that AB has a maximum torque of 6 and CD has a maximum torque. It's minus 6, but really it's really a convention which makes it minus 6. The torque is actually 6. So AB and CD have the same stress, or sorry, same torque. Tau AB equals tau CD equals 6 kilonewton meter. What this means is that you really don't need to design based on, both of them will give you the same design, because there's nothing here which is different from AB and CD have the same torque, and the criteria, that is the design criteria, is the same. So it has to be that both of them, you can use either of them to design the diameter, and that should be the final answer. So let's use this torque to compute the maximum, or compute the diameter possible given the shear stress, maximum shear stress 65 MPa. So this is a reverse calculation we've done so far. We've always solved for tau max given torque. In this case, sorry, we've not really computed diameter in any of this problem so far. So this is a problem where you're given the maximum shear stress and you're given the torque which is carried by this, in probably in application we need to find what is the diameter. So the formula is torque equals J times tau max divided by the diameter. So the diameter is, sorry, so the radius. So the radius is, so it's normally C outer, right? But C outer is going to be uh, T0 divided by 2. Okay. Okay, so what is J? We can again look at the appendix. It is pi T outer raised to 4 divided by 32. Okay, let's just confirm this. Or did I close it? I think I closed yeah, it's pi D raised to 4 divided by 32, where D is the outer diameter. So that's what it is. So this is right, so it's the outer diameter. So let's sub this value there to get pi D0 raised to 4 divided by 32. Now max divided by D0 divided by 2. And you should see that 16 pi D cube. Now max. No, this is not right. 16 is down below 16, right? I think that's right. D0, yeah. Yeah, so this is the formula. So if you want, you can remember this formula, or you can just derive it as I've derived it right now. So 65 megapascals. So mega converted back to, uh, remove the mega in the calculation. Pi d0 is an unknown. 16 tau max. Sorry, I did a mistake. This is not six. This is not the maximum torque. This is the maximum shear stress. So it should be 65 times 10 to the 6, and then the torque should be 6 kilonewton. 6 times 10 to the 3 torque. Yeah. So if you substitute and take the cube root of whatever you get after moving things around, you get diameter equals 77.8 millimeters. Okay. There is nothing competing here with this designs. Normally we had another problem we talked about, normal stress and shear stress. Doesn't so the question, doesn't the length play a role? The length plays a role only in the shear strain and not in the shear stress. So if you look at the formula, the shear strain depends on the length, but it's not the torque. Now you could say that shear stress comes from the shear strain, and there the length factors in. But in the calculation we have the torque and shear stress. They don't really have a length involved in it. Which is very interesting. The length doesn't determine how much shear stress an element will bear. It's only dependent on the radius. That's what it is. Now, how if you want shear strain, then yes, it will depend on the length. It's a very good observation. Um, okay, uh, what we saw so far is torsion of a circular shaft like this one. Now, if you and you'll always see problems involving circular shafts. You will never usually see problems, at least in this course, of a non-circular shaft. But here is what happens if you take a non-circular shaft and you apply a torque. What will happen is it will warp. It will warp in such a way that plane sections will not remain plane. So what you see here is this yellow part, which is a section of the cut of the beam. If you torque it, then this no longer is along the. So if this is, see, this is the XY plane. Let's call this XY. So this is what in this plane, this yellow section is in this plane. What happens is when you torque it, you will see that it'll actually move in the Z plane. So this will be uh, Z axis. It will bulge out in the Z axis. This is a problem with which happens only if you have a non-circular section. A circular section will never extend or elongate in the z direction due to a torque. And this actually makes our life hard. We cannot do many of the interesting things we can do with simple math. So we will not really study how to calculate the torque or do the derivation of torque for, sorry, the shear stress for this by using a derivation. We will not derive this because this derivation is beyond this course. What we'll do instead is we will use an empirical formulas which probably came from a physics-based calculation. So if you have a beam which is rectangular, okay, we're not doing any other shape, just rectangular, that's it, then you can write the maximum shear stress in terms of torque and the dimensions using this formula. So here in this formula, B and C, so we have B and C, these are dimensions of the rectangle. However, this factor alpha is a constant which is available in a table. So for different ratios of B to C, which is breadth divided by height, you will have different alpha. So this is, I would say this comes from a derivation, but the derivation is beyond this course. And then if you want to compute the angle of twist, theta, then there is another factor, beta, which also is sitting in here. It depends on the ratio of B to C. So T will be from the external torque. Tau max usually is given to you, or it's something you need to find. B and C are dimensions. G is modulus of rigidity, L is length. You can compute the value for tau max and theta using this formula. We will not go beyond this. We will not really do too much of non-circular sections. Okay. Any questions on this? We are okay. No questions. Okay, so let's move on to shear stresses in thin sections. Okay, now this is kind of interesting. Uh, we looked at hollow shafts, and we're going to look at thin wall tubes. Okay, the question is, when does a hollow shaft become a thin wall tube? What I mean by that is, what we're looking now is is something which looks on the left, but we also looked at shafts like this, C outer, C inner. Okay, sorry, other way. C outer is the this drive properly. So okay, so this is C outer, this is C inner, the inner one. We looked at torques applied to this kind of shafts, and we looked at torque. We're going to look at torques on these kinds of shafts, which are shown there. So here the thing is the thickness is basically the half of C outer minus C inner, right? If thickness is much smaller than, I don't know, this is really heuristic. So when would you use the formulas in this section? When will you use the formulas given the other section? Well, uh, a thumb rule could be, you could say if T is less than uh, 5 times 5 times, sorry, if you would say if T is very small compared to, so let's say it's 5 times T is C0 or 10 times T is C0, then probably you'll use the formulas here. There's no real hard and fast rule, but this is like an approximation to the actual cylinder, which has a reasonably big thickness. So here the thickness is large. It's probably comparable to the radius C0, then you will not use the formula. If, however, if the thickness 10 times the thickness gives you C0, so it's very thin, then you'll use the formulas here. So this section talks about how to compute the torque when you have sections which are like this, which is a thin tube. Okay. Now the derivation basically has two parts to it. One is it says that how do you compute? Well, it tells you that for this particular case, when the thicknesses are small, the shear stress times the thickness is actually a constant. Okay, so that follows from a derivation which is here. This formula is not very much used. The formula which you really use is the next one, which is basically telling you how is the torque. So T is the torque is related to the shear stress, like we've seen before. So here we have the final formula. Shear stress depends on torque, it depends on thickness, it depends on cross section area. Now this area is the area shown in yellow. So what you do is you take the thickness, you draw the median line, which is shown by the blue dashed line, and the area between in that median line is actually the area. Okay, and then if you want the angle of twist, is actually angular twist. So this is very important. This is angular twist per unit length is given by this formula. In this derivation, there is something which, if you want, you can follow this, but there's something which comes out like this integral comes out to be 2a, and I've given you the reasoning why it is 2a. It's basically area of a sector, and the area of a sector is half. So area of sector is approximately the area of a triangle, and that has a half factor of half. So there's a common confusion why there's a 2 here and why it is not just a, and that's because of the area of it. I've put it on here. You really don't need to know anything about the derivation. Just know that the shear stress depends on the torque in this formula. This is the most widely used formula in this section. And then, of course, if you want to know the angle of twist, that's the formula. So these are the two things you need to know in order to solve problems in this particular section. So what we'll do next is we'll actually use this formula and see if we can solve a couple of problems. I think just maybe just one problem. Okay. So here is uh, two sections. We need to compute the shearing stress. So tau in each of the four walls of the two tubings when it is subject to a torque of 24 kip H. So we need to find the shear stress, but we need to find the shear stress in all four sections. So what it means is we need to find the shear stress in AB. So A, B, which is unknown, BC, unknown, tau BD. Sorry, there's no BC. My bad. There's a AB, there's a AC, there's a BD, and there's a CD. Okay, you see that the way they are different is that this is a uniform thickness section. It is 0.16 throughout, and this one is 0.12 with the thickness for two parts of the thin beam, and it's zero point 0.2 for the other two parts. So it's slightly different. So the question is, will that matter? We'll see if that matters in this problem. Okay, let's call them A and B, A and B, and then solve for the shear stresses in A and B. And of course, you need to find four stresses for each problem. Okay. Okay, one sec. Okay, so what's the formula we have for this is that first of all, uh, we notice that this is going to be 0.16. This looks like it is couple of times, so 0.16 or even point, let's take zero point 0.2. So we have zero point 0.2 is the thickness, and we have what? The minimum dimension is 2.5. So this is at least 10 or 12 times. So 12 times approximately, it's a little more than 12. 12 times thickness. So 12 times the thickness, which is equal to 12 times 0.2 is approximately 2.5, right? 12, so 2.5 being one of the dimensions. So we can say that this is actually a thin beam, and we can use a thin beam formula. Okay. Okay, that's just we're given to here, but that's how the reasoning will follow. So we given that, now let's see the formula for the shear stress. It is right here. So shear stress is T divided by 2, 2 times T, uppercase T divided by 2 times lowercase t times A. Okay. So shear stress is T divided by uppercase T divided by 2 times lowercase t times A. Okay. Okay, let's take the first section. Okay, and then okay, and then remember the for the area, let's put the dimensions for 2.5 was 4, 2.4, 2.5, and then 0.16. Okay, now remember that for the area, we have to get the median line. So let's draw the median line. And then for the area, we're just interested in this area. Okay. Okay, so now area is this. It's going to be 4 minus, so we need to take half of 0.16 here and half of 0.16 here, right? So 0.08, 0.08, it all boils down to 0.16. 2 times 0.08 is 0.16. And then 2.5 times the same thing. We'll do 0.16 up and 0.16, sorry, half of 0.16 up and half of 0.16 down. So it's going to be 0.16, in all. This is going to be the area. And the answer for that area is, the area comes out to be 3.84 times 2.34. Okay, I don't seem to have done the calculation, but let's just keep it that way. The thickness, okay, so there is A, B, C, D. Now the thickness will depend on which section. So in turns out in this problem, AB, BC, AB, BD, DC, and CA have the same thickness. So really there's only one thickness here. We'll see that will change for the next problem. And then the torque is given to us 24 kipinch. 24, 20. Let me put our units. Okay, so we can say that the shear stress in AB equals shear stress in BD equals shear stress in DC equals shear stress in CA. And this is only true because the thickness is the same. They have the same. The only thing which is going to be different for the two problems is going to be the thickness, because area is going to be the same, torque is going to be the same. The thickness is the same, so we have the same shear stress. So it's going to be T, which is 24 divided by 2 times thickness, 0.16 times 3.84 times 2.34, 24, and this comes out to be DC equals tau C, 8.35 KSI. Okay, so that's was pretty straightforward. Let's do the second one, which is more interesting because now we're dealing with a non-uniform thickness. The thickness is not the same for all uh, for different parts of the beam. Okay, so I'm going to redraw that one. Yeah, I'm going to exaggerate this so it's a bit more easier to see it. Okay, so it's exaggerated in 2 dimensions in all four really. This thickness is 0.16, and this thickness is clearly is much bigger than twice of this, but I'm just going to put 0.2, so it's obvious that this is a different thickness. And then we'll draw the median line like before. Okay, and we need to compute this area. Same, which we need to see what it comes out to, and we know this is 4 and this is 2.5. That doesn't change. Okay, the formula is, well, let's just put A, B, T, and C. Okay, so the formula is tau equals T, uppercase T divided by 2 times lowercase t times A. Okay, let's compute what A is. Okay, so A is going to be 4 minus, okay, now you can see this part is 0.16. It's actually half of 0.16. And the right side is half of 0.2. So this is going to give me uh, the the base, the distance from C to D, that is along the median line. If you want the height, it's going to be 2.5 minus, again, 0.16, half of 0.16 divided by 2 minus half of 0.2. So this is 4 minus 0.08 minus 0.1, 2.5 minus 0.08 minus 0.1. Okay, so 4 minus uh, oh, my bad. This is 0.12. Sorry about that. I should have been more careful. It's 0.12. So just wondering, something was not right. This is 0.12. I copied it incorrectly. This is 0.12. So there's a slight change here. Just have to substitute this with the, and of course, this will change. 0.12, 1206, and 06. Okay, now if you do the math on this, it turns out that you will actually get something very similar to what we've seen so far. So this thing over here comes out to 3.84, and then this comes out to be 2.34. Okay, this is identical to the area in the first part, 3.84 and 2.34. Okay, it's just the way the problem is designed. The areas are the same. Okay, so if the areas are the same, is the stress going to be the same? The answer is no, because the thicknesses are different. So let's see what you get. So we see that AC and AB have the same thickness. So tau AC equals tau AB will be T would be 24 divided by 2 times thickness of AB, and AC is 0.12, and the area is the same as we got before, 3.84, 2.34. Okay, so this comes out to be 11.13, and then the other BD and CD have the same thickness of 0.2. BD have the same thickness as CD. It is 24 times 2 times thickness, 0.2, the same area. That comes out to be 6.68. So I'll just circle these. Maybe I should put the units. So it's KSI for the units. KSI. The other one is 6.68 KSI. So, okay, those are the answers, but let's just think about this for a minute. We have a problem which is very symmetric. The first part is symmetric. The second part is not symmetric. The thicknesses are not symmetric. It has 0.2 and 0.12 as the dimensions. Both of them give the same cross-section area. So essentially in this formula, uh, T and A are the same, but the thicknesses are different. The first part, all thicknesses are the same. So you get the same stresses for all parts. For the second part, the differentiating factor is two of these sections have 0.12 and two of them have 0.2. So when you compute the shear stress, you will see that we have for the thinnest section, so for the second one for 0.12, we have the minimum stress of what, 6.68. Then we have 8.35, I think it's here, 8.35 for this section, so for part B. And then we have for this 0.2 part, we have 11.13. So in other words, the thinner the section is, the higher is going to be the stress. Sorry, in this case, sorry, my bad. Yeah, sorry, I was right. So thinner the section is, so thinner, this is the thinnest one, is going to have the highest stress, and the thickest one is going to have minimum stress. And this correlates with everything we've seen in the class. The bigger the shaft diameter, the larger the area over which the force can redistribute, and you'll have less stress. So you always want to have a big thickness to have less stress. The, the consequence of this is that you need more material. More material usually means more cost, and it's going to be more expensive. And one more thing which I usually make a point is that if you're a mechanical engineer and you're going to put something like this on an automobile or a plane, then let's say you added 1 kilogram more. That 1 kilogram will move around for miles and miles. For a plane, it's going to be several million miles. For a car, it might be several thousand miles, 100,000, 200,000 miles. Every single kg you're going to carry over, you're going to basically spend in terms of fuel cost, and you'll see that that money will just add on. So what happens is there's a big incentive to reduce the weight to a minimum, but the moment you reduce the weight, the thickness and the dimensions reduce. But then you will be fighting against stresses. It's going to break early, and then for planes, for example, you don't want it to fly or break in midair. So you have to be very conscious of costs on one side, make it light as you want as possible, but then at the same time you want to be aware that the lighter it is, the more less material you use, the more prone it is to stresses and failure. Okay.